Addition reactions can also occur by free radical mechanism. If you will remember, the addition of HBr in an alkene generates a Markovnikov product. But in the presence of a peroxide, anti-Markovnikov addition of HBr occurs. This process is through a free radical mechanism. Typically, when exposed to air, alkenes readily form peroxides, and this impurity can cause a reversal of the radioselectivity of its reaction with HBr. The product is anti-Markovnikov. Bromine is added to the carbon with more hydrogens. How does this occur? Peroxides in the presence of heat or light can dissociate to form the alkoxyl radical. This radical may interact with hydrogen bromide in a free radical mechanism to form the alcohol and the bromine radical. This bromine radical can interact with a double bond to form a radical at the more stable position. In the case of my example here, the radical is more stable at the tertiary position, so bromine becomes attached to the carbon that has more hydrogen. This radical will abstract this proton from HBr to form another bromine radical and the product. This bromine radical will undergo another cycle in its reaction with the alkene. And so, we have a product that is opposite that of hydrohalogenation. Take note that hydrogen fluoride, hydrogen chloride, and hydrogen iodide do not behave in similar manner. Free radical reactions also occur in allylic halogenation. This reaction happens at high temperature or with a radical initiator and at low concentration of chlorine or bromine. As already discussed in alkanes, at high temperature, a homolytic cleavage occurs for chlorine and bromine to form two halogen radicals. These halogen radicals may interact with the sp3 carbon right next to a double bond. This hydrogen is allylic and will be taken by this radical to form this hydrogen halide and this allyl radical. This allyl radical is stable because of resonance, and this radical can again interact with another molecule of the halogen via a free radical mechanism to form the allyl halide. This halogen radical species can participate in another cycle of this free radical reaction. And so, when you react propene with chlorine at 400 degrees C, allylic halogenation occurs. Chlorine becomes attached to the sp3 carbon right next to the double bond. This compound here, N-bromosuccinimide, can be used to generate low concentration of bromine molecules. And in the presence of light or peroxides, bromine becomes attached at the allylic position, here or here, to form the allylic bromide. N-bromosuccinimide forms a small amount of bromine radicals, which abstracts the allylic hydrogen to generate HBr. Once HBr is generated, N-bromosuccinimide will react to form this compound and the bromine molecule. with HBr concentration kept low. Every molecule of HBr formed by the allylic halogenation reaction can react with N-bromosuccinimide to generate small amounts of bromine molecules, which can participate in the cycle. The relative stability of carbon radicals can now involve the allylic radicals. They are more stable than tertiary radicals, and the least stable are the vinylic radicals. The stability of the allylic radicals can be explained by molecular orbital theory and resonance. Molecular orbital theory is discussed in higher chemistry, so I will just show here for resonance. This allyl radical can have two different resonance forms due to transfer of electrons from the adjacent double bonds. This provides stability to this kind of species.